Okay, hello. So today I'm going to do a video about quotient modules, or I guess maybe a little bit about quotients in general, including quotient sets and quotient modules. Um, Let me share my screen before I start talking. I'm going to try to, from here on out, kind of, I'm going to try to shorten my videos a little bit in the following way, which is we've covered all of the kind of important algebraic structures that we'll need later. But sort of the most general, the one that includes the most other ones, is modules. Because remember, rings, a ring R is a module over itself. So a ring R is an R module. We also know that a vector space, V, is a module over a field. So if we do R modules, we've also covered vector spaces. We've covered abelian groups, because an abelian group, G, is a Z module. So they're groups with a specific ring, Z. And we've covered fields, right? Fields are rings, so we've covered fields. Although there's some peculiarities with fields, maybe we'll get into later. So yeah, if we do R modules, we've covered a lot of the things. We don't get things about non-abelian groups, so there's some interesting things to do there, and we don't get things about algebras, so there's some interesting things to do there as well. But I'll try to do the rest of the stuff that I want to do just for modules, and then maybe we'll come back later to some other things. But first, let's start at the level of sets. So what's a quotient of sets? To do this, we need to remind you what an equivalence relation is. So I can take the quotient of a set by an equivalence relation. Remember that a relation tilde is just a subset of S cross S. If I want a relation on S, I take a subset of S cross S. And I write elements of this subset, S comma R. Instead of writing S comma R is an element of this subset, instead I write S is related to R. That means that S comma R is in this relation. And then it's an equivalence relation if it satisfies three properties: that it's reflexive, so every element S is related to itself; symmetric, meaning if S is related to R, then R is related to S; and transitive, which means that if S is related to R and R is related to X, then S is related to X. And so that's the definition of an equivalence relation. And when we have an equivalence relation, I can take the equivalence class of an element, little s in big S, and it consists of all the elements that are equivalent to it. So the equivalence class of little s is a set of elements in big S that are equivalent to little s. Okay, so those are all things from a previous video. Now we can define the quotient of the set S by this equivalence relation. And it does really need to be an equivalence relation because it needs to be transitive and have these equivalence classes that are defined. The quotient of S by tilde is the set of equivalence classes. Okay, and it's also a set. So let's just do a kind of silly example of this. Suppose I have a set that consists of elements that are different colors. So maybe it's an element and a color. And I can define an equivalence relation on this set by saying X is equivalent to Y if and only if X is the same color as Y. That's an equivalence relation. And the equivalence classes, let's do an example of an equivalence class. So the equivalence class of X is all of the elements that are the same color as X. So it's all the orange ones, X, Y, and D. Or that's the equivalence class of X. Whoops. And then we have three other we have two other equivalence classes. We have the one that contains AB, the one that contains ZC. And so the quotient set, S divided by tilde, will consist of three different elements. One of them is the class that contains X, Y, and D. Another one is the class that contains A and B. Oops. Excuse me. And another one is the class that contains C and Z. Okay. So pretty much we've taken our element that contains 7 sets, and we identify some of them, and we get a smaller set. Now it just contains 3 elements. So we've collapsed some elements into each other. And we can also write this as, we can pick a representative of each equivalence class. So I can write it as the class of X, the class of A, and the class of C. Those are representatives. It doesn't matter which one I pick because they're all equivalent. All right. And maybe I can also just label them by the color. We have a blue one. We have a green one. We have an orange one. All right. Now, whenever you have a quotient set, you get a quotient map. So you get a special kind of map. It's actually not a special kind of map. It's just a map. And it always happens to be surjective. And how do I define this map? I define a map from S, the original set, to the quotient set by setting each element to its equivalence class. And this is a well-defined map. It's a function. Maybe let's do it for the example. So for the example, in the original set, I had X, Y, D. I had A and B. I had Z and C. And then in the quotient set, I only had 3 elements. I had the orange one, the blue one, and the green one. And the quotient map it sends A and B both to the green one. And it sends X, Y, and D all to the orange one. And it sends Z and C to the blue one. That's what we're defining Q to be. So here's S divided by tilde. Now note that Q is always surjective because every equivalence class comes from some element, because S divided by tilde is equivalence classes of elements of S. So Q is a surjective function. Okay. Now another definition is we say that a function is tilde invariant. Tilde is some equivalence relation. A function from S to T is tilde invariant if whenever S is equivalent to R for 2 elements of S, we have that f of S equals f of R. So basically, saying that it's tilde invariant means that the function respects the equivalence relation and it sends equivalent elements to the same place. Now, whenever you have such a function, what we can do is we can define a function out of S divided by tilde. And in fact, this is the universal property that defines what a quotient is. So this part might be confusing, but that's okay. The universal property of the quotient, it says that for any function, f from S to T, which is tilde invariant, there exists a unique function f bar from S divided by tilde to the same domain as f, t. Such that, and so this diagram is telling me, well, I'll explain the diagram in a second. So, and there exists a unique function f bar such that f bar composed with q equals f. So basically, if I take f of something, then f bar should give me f bar in that equivalence class should give me whatever. Here, I'll just write it down. If I have like s in s, then q of s equals the equivalence class of s, and then f bar on s should then be f of s. And this function is uniquely defined by this tilde invariant function. So I'll circle the quantifiers here. Here there exists this unique function f bar for any function that you give me f, as long as it's tilde invariant. And the reason I wrote it like this is because the function satisfies that if you go down here and then up here, and you follow that arrow from s to t, you get the same result as following this arrow, f, from s to t, so that the two paths are equal. We say that the diagram commutes. It's a good way to remember the definition, basically. Just think of it as a nice picture. Okay, so let's maybe prove this, or at least prove that there exists a unique function like this. So if f from s to t is tilde invariant, that means that if s is equivalent to r, then f of s equals f of r. And then define this function f bar from s divided by tilde to t by taking the equivalence class of s and just mapping it to f of s. Now, normally, this might not be a function. In other words, it might not be well defined because this is an equivalence class. So I could pick something that's equivalent to s, like maybe r, and I can map, this map would send it to f of r. And a priori, maybe f of s is not equal to f of r, but the definition tells us it's exactly equal because since it's f invariant, if the equivalence class of s equals the equivalence class of r, then f bar of the equivalence class of s, which is f of s, equals f of r, which is f bar of the equivalence class of r. And so this is really a function. For every input value, we get a unique output value. We don't have the same input value giving us two different f of r and f of s. They're the same. So f tilde is really a function. Is a function. And then I also claim that it's unique, and I can't really prove that it's unique with the tools that we have right now, but I'm going to tell you a fact, and I just hope you'll believe it. So it's an alternative definition of surjective, or an onto map. So Q is surjective. That means that if I have f bar composed with q, and it equals h composed with q for some other function h, then f bar equals h. And that's like an alternative definition of being surjective. It means if you take two maps, let's say here was q, and it went to s over tilde. Yeah. Okay, and then here was f f bar and h bar, or f bar and h, both went to t. If I have two functions like this, q is surjective if and only if whenever this path and this path are equal, we have that these two functions are equal. That's an alternative definition of surjective. So the fact that the quotient map is surjective tells you that this is unique. And you might also believe it's unique just because that's pretty much the only way that you can define a function that satisfies this property. Okay, so hopefully we're done with the confusing part of the video. Now let's get back to more down-to-earth thing. Let's do quotient modules. So a quotient module, like you might guess, is going to be a quotient set with some module structure on it. So let M be an R module, and N be an R submodule. Remember that being a module, one of the things is that M plus is an abelian group. And then we also have this scalar multiplication by elements of R. And we can define an equivalence relation on M by saying that two elements of M are equivalent if and only if their difference is in N. So it depends on the submodule you pick. And then the equivalence classes of an element little m are going to be all the things of the form m plus n. And the reason is, right, m, if I have m plus n minus some other m plus n prime, then that is going to equal n minus n prime, and it's going to be an n. And also an important thing to note is that when I divide by n, basically what I'm doing is I'm setting all of the elements of n to be 0. Because m, let's say that n is in n, then n minus 0 is in n. And so n is equivalent to 0. So everything in n is going to get squished into one equivalence class, namely the class of 0. Okay, so this is what the equivalence classes of that equivalence relation look like. And sometimes they're given a fancy name. Okay, so since it's all of the things of the form m plus n, a notation for this is to just write it little m plus big N. So that just means little m plus anything in big N. And these things are called cosets. So it's the coset of n by the element m. And then the quotient module of m by n is the set of all of these cosets. So it's the set of all the equivalence classes. And I can't believe I didn't write down an example of this, so let's do one. In fact, I probably should do this one anyway. So let's do an example of a quotient module. Let's let m be z. Remember that z is a module over itself, for sure. And then let n be 3z. 3z is a z submodule of z. So that's good. And let me just write out, so we know what z is, it's all the integers. So we've got like 0, we have 1, we have -1, we have 2, we have -2, we have 3, we have 4, we have -3, we have -4, -5, -6, etc. forever. 5 and 6, etc. forever. And then 3z means all the multiples of 3. So 0, 3, 6. Whoops, that's a bad 6. 6, 9, etc. -3, -6, -9, etc. Okay, and if we want to define the quotient module z divided by 3z, so we're going to identify all the things where their difference is in 3z. So for instance, 2 well, let's write this down here. 2 is going to be equivalent to 5 because 5 minus 2 is 3, and that's in 3z. And for instance, 0 is going to be equivalent to 3, and it's also going to be equivalent to minus 3 because those differences are in 3z, and it's going to be equivalent to 6, and so on. And 1 is going to be equivalent to 4, and it's going to be equivalent to minus 2, and it's going to be equivalent to 7, and so on. And actually, let's circle. If I circle all the elements that are going to be equivalent to 3, I get 0, I get 3, I get 6, etc. Minus 3, minus 6, etc. 1 is equivalent to 4, it's equivalent to 7, etc. It's equivalent to minus 2, it's equivalent to minus 5. And then 2 is equivalent to minus 1 and minus 4 and 5. And you see that I get this sort of repeating pattern of colors there. And so I can identify everything down into 3 different groups: the things that are 0 mod 3, the things that are 1 mod 3, and the things that are 2 mod 3. So we have 3 equivalence classes. So z mod 3z consists of the set, the equivalence class of 0, the equivalence class of 1, and the equivalence class of 2. And also maybe I should be writing them in the notation I just defined. So this is the same as the coset 0 plus 3z, 1 plus 3z, 2 plus 3z, blah, blah, blah. And one thing you'll notice about this quotient module is it's still a module. I can add elements of it. So let's see how to do that in general, and let's look at the example. So if I take a quotient module, it's still a module because I can add cosets by defining the addition to be like this. If I add the coset of m and the coset of h, I just take the coset of m plus h. And if I take the scalar multiple of r by this coset, I just take the coset of the scalar multiplication of r times m. So there's a straightforward way to define the multiplication, the scalar multiplication and addition on the cosets. So for example, 0 plus 1 is going to be the class of 0 plus 1, which is going to be the class of 1. Or like maybe 1 plus 2 is going to be the class of 1 plus 2, which is going to be 3, but that's equivalent to 0. And then I can also scalar multiply by any integer, maybe like minus 17 times the class of 2 is going to be the class of minus 17 times 2. That's the multiplication in z. So that's the class of minus 34. And I can take out any multiples of 3, so this is the same as the class of minus 1, which is the same as the class of 2. So that's how the multiplication and addition works. You still get a module, is the point. And then you get a quotient map. But now the quotient map isn't just a map of sets, it's actually a module homomorphism. And you can check that. So remember a module homomorphism, if I take 2 elements, m and h, the quotient map should send this to q of m plus q of h. But by definition, it sends it to this coset m plus h plus n. And by the way, I just told you that we define the addition on cosets. This is m plus n plus h plus n, these 2 cosets. But this is q of m, and the other one's q of h. So it's certainly an abelian group homomorphism. And then similarly, Q of R times M, where R is any element of the ring, is Rm plus N, which, by the way, I just told you how to scalar multiply a ring element by a coset, is R times M plus N, which is R times Q of N, or Q of M, I mean. So the quotient map is an R module homomorphism. And we also get the universal property of the quotient, but now for modules. So if for any module homomorphism now, f from M to P, which respects the equivalence relation, which now I'll call n invariant. I guess maybe I didn't clarify this point, but now instead of writing m divided by tilde, I'm writing m divided by n, because tilde was an equivalence relation that was defined in terms of the difference of two things lying in n. But yeah, now our universal property says if I have a function that's n invariant, and n invariant means that if m minus h is in n, then f of m equals f of h, then for the exact same reason I said before, we can define we have a well-defined function out of the quotient m divided by n, such that this composition holds. Okay, so now let's just do a couple examples. So examples of quotient modules. What happens if you divide m by the entirety of m? So in that case, the equivalence relation is m is equivalent to m prime if and only if m minus m prime is in M. But M is a module, and so it's an abelian group. So M minus M prime is always in M. So this is no condition. Every element is equivalent to every other element. And so this, if you divide by M, everything collapses into one equivalence class. And so the result is just everything is equivalent to 0. Okay? Or yeah, maybe a better way to write this is M minus 0 is in M for all M. So everything's equivalent to 0. So M divided by M is the 0 module. And now if I divide by 0, sort of the opposite thing happens. Now the equivalence relation is M is equivalent to M prime if and only if M minus M prime is in the 0 submodule. Well, 0 is the only thing in the 0 submodule, so that means M minus M prime is 0. But that means that M equals M prime. So the only thing that's equivalent to M is M itself. So all the equivalence class of M just consists of M. There's nothing else in it. And so we didn't identify any elements, so the result is just M. Okay, and now let's use these two things to do a slightly more interesting example. Let's go to the next page. Let me copy this. Yeah, okay, it copied weird, but that's okay. So M is Z2, meaning the Cartesian product of two copies of Z. So it should be pairs of M comma N, where M and N are in Z. And then we have a Z submodule of this that consists of pairs but the second one is 0. So this is a submodule that's isomorphic to Z. It's just 0 in the second component. Now let's see what happens if I try to do Z squared divided by Z cross 0. So the equivalence relation is m comma n is equivalent to m prime comma n prime if and only if m. Okay, so remember the addition in z squared is component wise. So if I take this one minus this one, what I get is m minus m prime comma n minus n prime. And this is supposed to be in the submodule that we're taking the quotient by. So it should be in z cross 0. So that means that m minus m prime should be in z, and n minus n prime should be in 0. But we just saw this is no condition at all, and this means that every element is only equivalent to itself. So what we get is z squared divided by z cross 0 is a set of things in here. Everything gets identified. So we have z quotient by z. And in this slot, let me do it in different colors maybe. That'd be good. No, I'm not going to do it. Okay. Underline this, underline that. Okay, and now in this slot, nothing gets identified. So we have z divided by 0. And so we just saw that this one is 0, and this one is z. So the quotient of z squared by a submodule that's isomorphic to z is just a copy of z, which is kind of what you would expect. Now let's actually do another example. Let's do vector spaces. They work the exact same way. Except now I'm not going to do it explicitly. I'm just going to do it up to isomorphism. So let V be a R vector space. And let's just suppose, because every vector space is isomorphic to some R to the n. So let's say V is R to the 7, or it's isomorphic to that. And W some subspace, a vector subspace of V. Let's say W is isomorphic to R to the 3. Then if I take the quotient of V by W, with kind of by the same argument I just did here, except only up to isomorphism. Okay. So R7 divided by R3 by the same argument as above is going to be basically isomorphic to R to the 4, because you're going to get 4 copies of R divided by 0 and 3 copies of R divided by R. And this is a general thing, actually. If we've talked about these too, the free modules. Free modules work very nicely. These are the things of the form, if we're looking at free modules over the ring R, these are the things of the form R to the n, where they're just n copies of R with component-wise scalar multiplication and addition. And if I take the quotient of R to the n by R to the m, where m is less than n, it's going to be isomorphic as an R module to R to the n minus m. That's what we just did. We did it here for vector spaces. Vector spaces are free. R vectors, real vector spaces are free modules over the real numbers, and copies of powers of z are free z modules. All right, one more example just to tease the next video, which is an example of a quotient module that's a little bit less trivial. Let's take R to be the polynomial ring, R of x. So these are real polynomials. it's the set of all the things of the form a0 plus a1x plus a2x squared plus dot, dot, dot. So you have coefficients in the real numbers, and then they're coefficients of powers of x, real polynomials. And then n is going to be the submodule, or in ring language, the ideal generated by the polynomial x squared plus 1. So that means n is going to be the set of all the things that have x squared plus 1 as a factor. So they're going to be x squared plus 1 times some polynomial. Well, I'm going to claim, and we'll prove this in a future video, that m divided by n is isomorphic to the complex numbers. And you can intuitively see why this should be, because if I divide by n, if I take r of x divided by x squared plus 1, right, in the equivalence relation, what we're doing is we're setting all the things in this submodule to be 0. So in particular, x squared plus 1 should be 0. And if x squared plus 1 equals 0, then x squared equals minus 1, and then x equals the square root of minus 1, or I. And so what we should get is kind of r adjoin I, which is the complex numbers. So, or maybe I should write this not as a polynomial ring, kind of like this, r adjoin I. So that's a teaser. We'll show how you can prove this in the next video when we talk about the first isomorphism theorem, or maybe the video after next.